Hi everyone, welcome back. In this section we're going to continue looking at functions of multiple variables, and in particular we're going to look at how to construct a tangent plane to the graph of a function of multiple variables at a single point, and we're going to look at linear approximation. So this is how to approximate a function by a linear function. And this is going to be tightly connected in with the idea of a tangent plane. You can think of this as sort of two sides of the same coin. We've got a tangent plane, which is a geometric construction. It's basically the plane you have in space that is tangent to the surface at a point, or best approximate the surface at a point. So we sort of got this geometric concept. On the other hand, if we take the function whose graph is the tangent plane, that's a linear function. And that function is what we call the linear approximation. So there's the geometric interpretation and the analytic interpretation. The geometric is the tangent plane itself. The analytic is the function that has a graph, which is the tangent plane. So all of this really boils down to just really understanding what a tangent plane is and how to construct it. So let's look at a reminder of what a plane is and how to describe a plane by its standard equation. So a plane in three-dimensional space. Draw a rough sketch of one here. We've got a point on it. Our point is given by coordinates x0, y0, and z0. For a plane, we have a normal vector, so we'll call that n, and in this particular case, we'll let the components be capital A, B, and C. Then for any point on the plane, just any arbitrary point, let's say its coordinates are x0 or xyz, sorry, not x0, but xyz. Then we can construct the vector that goes from the point P to this arbitrary point on the plane. This vector has to be parallel to the plane. It's got to live in the plane, and so it's got to be perpendicular to the normal vector. What are the components of this vector? They are x minus x0, y minus y0, z minus z0. That's the vector components, where we get them from taking the tip point minus the tail point. And the idea is these have to be perpendicular to each other, these two vectors, and so their dot product is 0, and their dot product is just this equation here. So that's the equation of the plane. It describes all points with components x, y, and z, or coordinates x, y, and z, that live on the plane. So now we can take this one step further. If c is non-zero, so if that value in front of the z minus z0 term is non-zero, then what we can do is we can solve this equation for z minus z0. So then we rewrite as well actually I'll just do the full rewritten version all in one go. What are we going to do? We're going to isolate the z minus z0 on one side. We're going to push everything else to the other side and divide by c. So we get capital A over c, negative capital A over c, times x minus x0, minus capital B over c, times y minus y0. Or we could write this as little a, x minus x0, plus little b, y minus y0, where little a is negative a over big A over c, and little b is negative big B over c. So we've just rewritten our equation of the plane in this form. And you may say, well, why did we write the equation of the plane in this form? Well, we're interested in finding a tangent plane to a point on a surface. So now what we'll do is we will consider a function z equals f of x, y, and a point x0, y0 in the domain. So once we have this function and this point in the domain, we can ask for example, the plane which best approximates the function at that particular point, well, at the point x0, y0, and f of x0, y0, so the point on the surface. In order to do that, we can appeal to some of our Calculus 1 ideas. So to get a visual for this, let's look at a 3D demonstration. So we've got our surface. That's our graph of our function f. We've got a point on it. This is essentially our point x naught, y naught, and then the function value f of x naught, y naught. And what we're interested in is trying to find the plane that best approximates the surface at that point. I will draw the plane in. This is the plane we're interested in trying to find. So how do we find this plane? Well, we break this down into a couple of Calculus 1 problems, a couple of functions of a single variable problem. First way is to slice our surface with a plane for some y value, in particular the y value corresponding to the y value of the point we're at. So this is the plane y equals y naught. Where that intersects the surface is a curve. That curve is now just, if we stare at that green plane, that curve, I mean I can even turn off the surface, that's just a curve in a plane. So this is a 1D calc problem. And now I could ask, for example, for the tangent line to this curve. What would the tangent line to this curve be? Well, it would be the line that passes through this point whose slope is given by the derivative of the function. Now what is the function that gives this curve? Well, it's the same function f that we have that generated the surface, except now we've got the y value is a constant, so it's f of x comma y naught. So it's just a function of x now. And when we take its derivative, well, that's just the x partial derivative. So we can get the slope of this line here by taking the x partial derivative of the original function. We can do the same thing for the other direction. We can say we're interested in how the surface intersects this plane. This is when x is a constant. Oops, I'm going to turn off the surface again. How do we get the equation of the tangent line there? Well, this is just z is a function of y, so z is equal to f of x naught y, and we can get its slope of the tangent line by taking its derivative. And that's how we get essentially the direction of this red vector, and in the other case the direction of the green vector. Those are just the partial derivatives. So that was another way, just revisiting this idea of a partial derivative, but seeing it in the context of the tangent plane. Okay, so what have we actually done here? Well, we've said let's consider the function at a particular point, and we're interested in the tangent plane. So what is the tangent plane? The tangent plane, well, this plane, we want it to intersect those two planes that we've been interested in. We'll go back to the demo again. We want the tangent plane, this purple plane, to intersect the green plane in the tangent line to the curve where x is changing but y is constant. And we also want the tangent plane to intersect the red plane in a line which is tangent to the curve where y is changing and x is constant. So the tangent plane, what is this? This plane intersects with y equals y naught in the line. So what is the line it intersects with? Well, we have the plane written up above here. So this would be our plane we're trying to find. We need to know what the a and b values are. That's really all we're searching for. What are those a and b values which make it a tangent plane, which make it a good approximation to the surface? Well, this plane intersects the plane y equals y naught in the line. We just plug y naught in for y into the equation. So this is the line of intersection. And this line should be the tangent line to the curve z equals f of x y naught. So now we're in a one-dimensional calculus problem, a calculus 1 problem. We've got this line has got to be the tangent line to this curve. So our input variable is x, our output variable is z. What does that mean? That means that that little a that's sitting up in our equation of our line has to be the derivative. So a has to be the derivative of our function f at x naught, y naught. And because x is our independent variable here, it's the one that's changing, it's got to be the x partial derivative. And so that's the first observation we can make now, is we're looking for a plane that does a good job of approximating the surface. We've just been able to decide that, hey, wait a minute, that has got to be the x partial derivative. Similarly, the same argument will show that b has to be the y partial derivative. And so that b there is going to be f sub y, x naught, y naught, in order to be the tangent plane. So that's how we can attack this problem of what's the plane that's the best approximation to the function at a point, by converting it to calculus 1 type problem. And so that gives rise to this definition of our tangent plane. Our tangent plane, suppose f has a continuous partial derivative, an equation of the tangent plane to the surface at a particular point, x naught, y naught, is given by this equation here. These were really the only two things we had to figure out. What were those values we put in front of the x minus x naught and the y minus y naught? You can see this very closely resembles the equation of a tangent line. It's just, if I was looking at the tangent line to a function z equals f of x, I'm just going to cancel out this thing, that would be the equation of the tangent line. All we're doing here is adding on an extra variable. We've got a function of two variables, so what's the tangent plane? It's the x derivative times the change in x plus the y derivative times the change in y. Okay, so that's one way to look at this problem. We can look at this in a slightly different way. We can look at it, instead of going back to calculus 1, we can use techniques from parametrized curves and get the same result. So I want to show you an alternate method to think about why the equation of the tangent plane involves these partial derivatives in precisely the spots they appeared. So here's an alternate way to look at the same problem. So we'll go back to our demo, and what we're thinking about now is the following. We've got our surface, we've got our point on our surface, we slice it with a plane, that produces this curve. The plane we're using is y equals y naught, that produces a curve. Now, in the calculus 1 idea, I said let's think about it as a curve just in the plane, so a plane curve. Now, in this alternate way, we'll think of it as just a space curve. So, because that's just a space curve, we can write it down using our vector functions. So let's say the curve in the plane, well, maybe I'll say intersection, I'll be very precise here. The curve of intersection between z equals f of x, y, and the plane y equals y naught is the following. It will be, we'll call it r sub 1 of, and because the y value is fixed, we're intersecting with the plane y equals y naught, then what's changing essentially is the x value. So we'll make it a curve that's parameterized by the x variable rather than going to some other variable t. So now x is allowed to change, y has to be constant, and the z value depends on those previous two values. So there's our parameterized curve, which gives us that curve of intersection. Then I can go ahead and look at what is the tangent vector at that particular point in question. This is the point we're trying to construct the tangent plane at. So what is one tangent vector to the surface at that point? Well, that would be the derivative of this. So that's r1 prime of x, and we'll do it right at the point x naught. So what's our derivative? Our derivative of x is 1. Our derivative of y naught, that's a constant, so that's 0. Our derivative of f, and notice y is a constant. X is the only variable we have for this function f in this third component. So when I take its derivative, I'm taking the x partial derivative of it and evaluating at x naught, y naught. So there's our tangent vector. So that's, in our demo here, that's that green vector. That's what we've just computed. That green vector, it has components 1, 0, and the x partial of f at that point. So those are our components. We do the same thing for the next direction. We'll go ahead and construct that red vector. So let's do that now. The curve of intersection, maybe I'll do it in a different color. Curve of intersection between the function itself, or the surface, and the plane x equals x naught is R2 of, in this case, y is allowed to change, x naught, or x is a fixed value, so it's x naught, y can change, and our z value depends on the previous two, so x naught and y. So that's our parameterization of that curve, which is the intersection of the plane and the surface. We can go ahead and construct its tangent vector. That's going to be R2 prime y, and we'll do y naught, so we'll evaluate it right at the point. So we'll take its derivative and then we'll evaluate. When we take its derivative, derivative of x naught is 0, derivative of y is 1. The derivative of the last component is the y partial derivative of f, and then we evaluate it at the point in question. So now we've got those two tangent vectors. There's one tangent vector, there's the other tangent vector. And what are we going to do? We're going to take those things and we're going to construct the normal to the surface at that point. I've got two directions which are tangent to the surface. Now I can construct its normal. Its normal is going to be the cross product of these two, r1 prime of x naught cross r2 prime of y naught. And we can use our mnemonic to write down what the calculation for the cross product would be. It would be 1, 0, f sub x, x naught, y naught, and 0, 1, f sub y, x naught, y naught. So when we do the calculation of the cross product, we get negative f sub x, x naught, y naught, negative f sub y, x naught, y naught, and 1. So that's a straightforward cross product calculation. You can verify that you get the same result. So that's our normal to our surface. And therefore, the tangent plane is, well, it's the x component of the normal vector times x minus x naught plus the y coordinate of the normal vector times y minus y naught plus the z coordinate of the normal vector times z minus z naught, and that's equal to 0. So just using the fact that we've got a point on the plane, a normal vector to the plane, so the dot product has to be 0, that's the equation of the plane. I wrote tangent, but I meant tangent plane. So now we can rearrange this a little bit. Let's solve for z minus z naught. Push everything else to the other side. That gives me an f sub x, x naught, y naught, x minus x naught, plus f sub y, x naught, y naught, y minus y naught. And so there's our rewritten form of our tangent plane. And that's the exact same as the plane we had up above in the formula. So we've verified the equation of this tangent plane and its relationship to the partial derivatives, f sub x and f sub y, in two different ways. One, we looked at it through the lens of calculus 1 and a function of a single variable. And two, we looked at it through the lens of space curves. And in both cases, we got the same result. That's our equation of the tangent plane. That's something that is definitely worth remembering. It's going to form the backbone of this entire topic. Tangent planes, linear approximation, and differentials. It's all tied up into all of those things. So let's do an example where we calculate the tangent plane. So we want to find the equation of the tangent plane to this surface at the point 1, negative 1, 1. So let's call this something. Well, first I'll write it out as 4 minus x squared minus 2y squared, and I'll put it to the power of a half. That way when I go to differentiate it, I can use the power rule. We'll call this thing f of x, y. So what are we interested in? To get the tangent plane, we need to know the x partial. So that's going to be 1/2 comes down, so that's 1 over 2, and then the square root gets pushed to the bottom. That's from the power rule. The exponent becomes a negative 1/2, so that's a square root in the denominator. And then we multiply by the derivative of the inside, so that's going to be a negative 2x. So we have a negative x over square root of 4 minus x squared minus 2y squared. We're really interested in the case where when the partial, or the value of the partial derivative at the point in question. And so we want to know what is f sub x at 1, negative 1. So we can plug 1 and negative 1 in. The top becomes negative 1. The bottom becomes 4 minus 1 minus 2. So 4 minus 3 is 1. Square root of 1 is 1. So there is our value. It's just negative 1 for the x partial. We can go ahead and do the y partial. Again, it's the derivative of the outside function, which is the square root. And then we multiply by the derivative of the inside function with respect to y, and so that's a negative 4y. And so this is negative 2y over the square root of 4 minus x squared minus 2y squared. We're interested in the value at 1, negative 1. The top becomes 2, the bottom is 1 still, and so our value is 2. So that means we can now work out what the tangent plane is. It's z minus the z coordinate of the point we know is equal to the x partial derivative times x minus the x coordinate of the point we know, plus the y partial times y minus the y coordinate of the point we know. Or in other words, z minus 1 is equal to negative x minus 1 plus 2 times y plus 1. So there is our equation of our tangent plane. If we want to put it in a simpler form, pushing all the variables to one side and constant to the other, we can do that. We can write it as z minus 1, negative x plus 1 plus 2y plus 2. Bring all of the variables to one side. X minus 2y plus z is equal to, push everything to the other side, is equal to 4. So there's an alternate way we could have expressed the tangent plane. Both are fine. We can do a quick double check at the one at the very end just to make sure. Does our point that we want it to pass through, as a very quick check just to see, did I make any silly algebraic or arithmetic mistakes? That point better live on this plane because that is the tangent plane through that point. So if we plug that point in, 1, negative 1, 1, we see that we get 1 plus 2 plus 1 is 4. Yeah, okay, so it lives on that plane at the very end. So that's a good sign. All right, so that's basic construction of tangent planes. So first just to recap, what we did was we introduced the idea of a tangent plane as this plane that at best approximates the function, and the function at that point, or I should say the surface at that point. We looked at it through the lens of Calculus 1, single variable, and we saw what the form of the plane had to be involving these partial derivatives of x and y. We took an alternate perspective and looked at it through the lens of parametric curves, and again saw that the equation of the tangent plane had to be the way we've written it down. So we justified this formula for the tangent plane at the top of the page in two different ways. So that is our tangent plane. Now we can go ahead and use that equation to construct tangent planes. And so we did an example where we had a surface and a particular point, and we constructed the tangent plane there. Next, what we're going to do is we're going to look at the tangent plane now as the graph of a function. And that's known as the linearization. And then we will look at linearization and linear approximation. So to construct the linearization of a function at a point, basically build off the idea of the tangent plane. So we had our function, in this example, that was the square root of 4 minus x squared minus 2y squared. From that, we built the equation of the tangent plane. Now, if I take this equation of the tangent plane and I just solve for the variable z, then what I get is that I recognize that the tangent plane is just the graph of this function. This function's a linear function, so I'll call it L of xy. And what this is this is a linear function whose graph is the tangent plane to f at the point in question, which was 1, negative 1, 1. So that was 1, negative 1, 1, as we can see at the top of the page. That was the point we constructed the tangent plane at. So we've just constructed a linear function which has a graph that's the tangent plane. So the idea here is we've taken our original function f, we constructed a tangent plane, and now we've constructed from the tangent plane a function whose graph is that tangent plane. Since the tangent plane is a good approximation to the surface at that point, then this linear function is a good approximation to our function f near that point. And this linear function is known as the linearization. So it's a linear function that's a good approximation of the function itself near that point. So what is our definition of linearization? It is we start with a function f and we assume it has continuous partial derivatives at the point ab. The linear function whose graph is the tangent plane to the graph of the function f at the point in question is called the linearization. And so what we can see here is the linearization is really just the tangent plane where we've written it in the form of, I'll put this is equal to z, is we've essentially written z is equal to z naught plus the x derivative times the change in x plus the y derivative times the change in y. So if I put in the value for z and z naught in here, that's really the tangent plane. So all we're doing is saying that let's make it into a function. And now that's the linearization. When we use this linear function to approximate the function f itself near the point, that's a technique known as linear approximation. So here we've got our linearization, L of xy, and we can use that for values of xy near the point we took this linearization at. So for x and y near a and b, if I plug those values into the function L, what I get is values that come out that are pretty close to the values of the function evaluated at that same value x and y. So these linear values, the values that are coming out of this linear function, are close to the function values of f. And this is the technique of linear approximation, using a linear object to approximate something that could be more complicated. Let's see an example of this. We want to find the linear approximation to z, so to this function here at the point 1, 2. So just so we can talk about it, we'll let f of xy denote that function, and we're interested in finding a linear approximation to it. So our linear approximation, that's going to be involving or requiring us to compute the derivative, specifically at the point, or the partial derivatives at the point. So the x partial derivative is 6x minus 9y. So in particular, at the point 1, 2, we have 6x squared minus 9y. So at the point 1, 2, this is 6 minus 18, or negative 12. We need the y partial derivative as well. That's going to be 6y squared minus 9x. So in particular, at the point 1, 2, that's our y derivative. So at the point 1, 2, this is going to be 6 times 4, which is 24, minus 9, or 15. So the linearization is that function L of xy, which is given by the function value at 1, 2, plus the x derivative at 1, 2 times x minus the x coordinate of that point, plus the y derivative at 1, 2 times y minus the y coordinate of that point. F of 1, 2, so we plug 1, 2 into our function f, and we get 2 plus 16, so that's 18, minus 18, so that's 0. Then I get a minus 12, x minus 1, plus a 15 times y minus 2. Or in other words, it's negative 12, x minus 1, plus 15 times y minus 2. So that's our linearization. What that means is that, maybe we'll jot this down. This means that for x, y near 1, 2, the function value xy is approximately given by the values of this linear function. So I can use values of that linear function to approximate the values on the original function. What do we want to follow up? What's our follow-up question here? Well, we want to approximate the y-coordinate of the point, 1.1 and y, that belongs to this curve. So that follow-up question is we're interested in the curve. If we look closely at it, it's really just f of xy equal to 0. And so we want to find points x and y that satisfy this equation. In particular, we want to find the points. So we want to find y such that f of 1.1 y is equal to 0. Since we just want to approximate, so it's asking us just to approximate the y-coordinate, so we do this by finding y such that, well, our function f1.1 comma y is approximately given by the linearization. So I'm going to use my linearization in place of the function f. So I'm going to use L1.1 y equal to 0. And what is that? Well, now I can use my linearization above, so that's negative 12. 1.1 minus 1, or 0.1, plus 15 times y minus 2 is equal to 0. This is a linear equation, one variable, so we can solve it. That's the nice thing about using the linearization, is it produces a linear equation which is easy to solve, rather than the original equation, which would have been, well, it's a cubic in x's and y's. So in order to try to solve for a value, we'd have to perhaps solve a cubic polynomial, which is not an easy task to do. In this case, we've converted it to solving a linear problem. And so we could solve this problem, and we get that y is equal to 52 over 25, or in other words, 2 plus 2 over 25. And so there is our approximate value for y. Y has just got to be a little bit bigger than 2. It's 2 plus 2/25. Okay, so that was a technique of taking a function, finding its linearization, and then using its linearization in place of the function to solve for an equation, or solve for some values of the variable which have some desired property. All right, so that's it for the tangent plane linearization. What's next now is we're going to take a bit of a detour and talk about differentiability and the idea of a function being differentiable. And that's related to the tangent plane. So all these things are related to tangent planes. So we'll see how differentiability is defined in terms of tangent planes. And then we'll look at this concept of a differential. So we'll pick it up in the next part of this lecture.